Okay, so all right, it's my honor to chair the afternoon session. But before I start, I think I was told to ask you guys for permission to show your face on the video so that people on YouTube can see your beautiful faces. So whoever's not doing that, can you raise your hand or quietly leave? I don't know, maybe see it later or something. Yeah. I assume everyone's okay if nobody is. All right, so now we can start the first talk in the afternoon. So the first talk will be given by Professor, Dr. Lakshmi Priya from Tel Aviv University, Israel, and she's going to talk about nodal volumes of harmonic functions.
Thank you very much. Good afternoon, everyone. I just want to thank the organizers for this amazing opportunity. And, so today I'll speak about nodal volume of harmonic functions. This is work which Andrea, who was formerly a postdoc at Tel Aviv, and I did under Professor Sasha Loganov. So let's start with a simple question. Suppose you have a harmonic function in R2. You look at the zero set where the function vanishes. Can you say and assume that, so throughout this talk, we'll assume that all harmonic functions are non-constant. Can you say that the total nodal length, the total length of the zero set is infinite? The answer is very simple in this case. It is yes, because the zero set is going to be non-empty and it cannot have any bounded connected components as a consequence of the maximum principle. So your zero set is going to look something like this. It's going to be a bunch of infinite paths. So the total length of this is going to be infinite. Natarashvili asked the same question in higher dimensions. So if you take any harmonic function in dimension 3 or higher, and look at the zero set, can you say that the appropriate Hausdorff measure of this is infinite? It turns out that this question is not so simple. So let's see why. Let's see why the previous argument doesn't work. So first of all, in this case again, it is true that the zero set is not, and we will surely have an infinite component, but it could potentially look something like this. So in R3, so this is, we can think of this as an infinite bottle whose neck shrinks to 0 so that the total surface area of this is finite. So this question was open at least for 30 years until very recently, in 2016, Sasha resolved this conjecture in all dimensions. So he showed this by getting this following quantitative estimate. Suppose you take any harmonic function on this ball of radius 2 and assume that the harmonic function vanishes at the center. So he showed that there is a universal constant such that the nodal volume in this unit ball is bounded below by this universal constant. So this is enough to establish this conjecture because we'll be able to find countably many balls whose centers are on the zero set. So the total nodal volume is infinite. Sasha actually showed something much better than this estimate. We'll see what it is in a few slides from now. So today I want to present some refinement to this quantitative estimate which Sasha obtained in 2016. All right, so the first part of the talk is going to be like a warm-up, and we'll talk a little bit about harmonic functions and their zeros. So mostly we'll look at Rn and harmonic functions there. Sometimes we will also talk about smooth or analytic manifolds and Laplace eigenfunctions. So harmonic functions and Laplace eigenfunctions are close cousins of each other, and it makes sense to study them in parallel. So this is a concrete reason for why they are closely related. If we start with a Laplace eigenfunction on a manifold, we can define what is called its harmonic lift. So this is the function f tilde, which is f times exponential of square root lambda t. It's easy to see that this will be a harmonic function on this product manifold. So if we manage to prove things about harmonic functions, we can pull back and say useful analogous things about Laplace eigenfunctions. So let us talk a little bit about Laplace eigenfunctions and the zero set. So this is a picture of the nodal portrait of a Laplace eigenfunction on the two-dimensional sphere. So just a quick look at this picture gives us a feeling that, I have to say what this picture is. The black part is where the function is positive, and the gray part is where the function is negative. And the interface between these two regions is where your function vanishes. So just a quick look at this picture tells us that the zero set is very regular. The regularity of the zero set actually comes from the elliptic regularity of the Laplace eigenfunctions. So some of the interesting features of the zero set are the density and spread of the zero set, the number of components of the zero set, and finally, and what is most relevant for this talk is the total nodal volume, or in this case, the total length of the zero set. So let's take the simplest example of a manifold and look at how Laplace eigenfunctions behave there. So on S1, on the circle, we know that the eigenvalues are n square. The corresponding eigenspace is spanned by sine n theta and cos n theta. So this is a picture of a plot of the Laplace eigenfunction here from this space. So there are two interesting features of the zeros here. The first is the number of zeros is of the order of square root lambda. And the zeros are equidistributed here in this example. So the zero set is 1 over square root lambda dense. This 1 over square root lambda is what is called the wavelength scale.
It's called what?
A wavelength scale. Wavelength scale.
Oh,
So we can ask if these two properties are true on a general manifold. The density property is true. It is actually a simple consequence of Harnack's inequality. Yau conjectured that this an analogous property is true for more general smooth manifolds also. So he conjectured that the total nodal volume of a lambda Laplace eigenfunction grows like square root lambda. He made this conjecture for smooth manifolds. Dooley and Pfefferman resolved this conjecture in the analytic setting. Nothing was known for smooth manifolds until Sasha's work in 2016. He made significant progress in the smooth case also. Okay, let's talk about harmonic functions a bit. Again, harmonic functions also have a lot of regularity, and a non-trivial property of the zero set is that if we look at the singular zeros, that is where both the function and the gradient vanish, they are negligible in comparison to the zero set itself. Okay, so in dimension 2, we know that harmonic functions are just the real and imaginary parts of holomorphic functions. So they have such an analytic representation. We have an analogous representation in higher dimensions also. So similar to what is happening here, these angular parts are actually Laplace eigenfunctions on the unit sphere in Rn. Okay, so let's now talk about zeros. So how to quantify the nodal volume of a harmonic function? So in general, if your function is nice, the zeros are controlled by the growth and vice versa. So here are two simple examples. If you have a polynomial of degree n, it can have at most n zeros. And here is a local version of this. If you have a holomorphic function, so this is Jensen's formula. We can think of this as a measure of how much the function has grown from the small ball to the large ball. So this can be thought of as an estimate of the local growth. So this relates to the local zero count. So we expect that such a thing is also true for harmonic functions. So we want to study the nodal volume of harmonic functions in terms of its growth. But how to measure the growth of a harmonic function? So a useful notion of growth for harmonic functions and Laplace eigenfunctions is the doubling index. So how is it defined? If you take a ball B which is centered at P and radius R, by 2B we mean the ball with same center but twice the radius. The doubling index of U in this ball is defined to be log of this ratio. So this is the ratio of the supremum of U on the larger ball to its supremum on the smaller ball. So it tells us how much the function has grown from B to 2B. Okay, so let's take a very simple example and look at what is the doubling index. So if we take x to the n and r, it's easy to see that the doubling index at 0 at any scale is n. So somehow the doubling index picks up the order of vanishing at this point. So this is true for in a more general situation also. If you take a real analytic function, if you fix the point and ask for what is the limiting doubling index as the scale goes to 0, this is actually the order of vanishing of the function at this point. Okay, so here are again like one more example. If we take a harmonic polynomial and let's calculate the doubling index at 0, at small scales, the doubling index is, the dominant term is just the first one, so the doubling index is like m. At large scales, the last term is the dominant one, so the doubling index is like capital M. So the doubling index can be thought of as a notion of degree for a harmonic function. We want to now estimate the nodal volume in terms of its doubling index. So at this point, it is useful to compare what is known for harmonic functions and Laplace eigenfunctions about the nodal volume. So this first column is all based on work of Donnelly and Pfefferman from 1988. So the setting is they look at a lambda Laplace eigenfunction on a real analytic manifold. So they showed that the doubling index on any geodesic ball is bounded above by square root lambda. And they also get upper and lower bounds of square root lambda for the nodal volume. So what is the situation for harmonic functions? We take a harmonic function on 4 times b, where b is the unit ball in Rn. We also assume that the harmonic function vanishes at the center. So it follows from this work of Donnelly and Pfefferman that we have an upper bound for the nodal volume of U in B in terms of the doubling index of U in the ball B. So somehow in both these situations, upper bound is much simpler than the lower bound. The lower bound is the more tricky part. So what about the lower bound? So it was conjectured that the lower bound is the doubling index of a smaller ball, in this case half b. So Sasha actually, I said that Sasha obtained a lower bound of constant, a constant lower bound for this nodal volume, but he actually obtained something much better. He got this lower bound, which grows to infinity with n. So today I want to present this new result where we can show that we can come close enough to this conjectured lower bound. Okay, so all this is stated for the unit ball, but there's nothing really special about the unit ball. We can say, we can talk about any ball. For that, I need to introduce this new notation called the scale doubling index. The scale doubling index is just the doubling index times a scaling factor, r to the n minus 1, where r is the radius of the ball, because we expect the nodal volume to have this scaling if we scale the function. So in terms of this new notation, the upper bound for the nodal volume in B is the scale doubling index of B. This follows from the work of Donnelly and Pfefferman. And the conjectured lower bound is the scale doubling index of a smaller ball. Okay, so we are able to come close enough to this conjecture. So in the next part of the talk, I just want to give some heuristics and discuss some ideas for how we can hope to get, how we can hope to estimate the nodal volume of harmonic functions. So let's start with the simplest case, which is when the doubling index is small. So what is the situation? We have a ball. So we take a harmonic function which vanishes at the center of the ball and assume that the doubling index of u in this ball is bounded by a fixed constant. So it is quite easy to show that in this case, we precisely know what is the nodal volume in this ball. So up to constants, it is just going to be the scale doubling index of this ball, which is just r to the n minus 1. So in this case, there is nothing really to prove. The difficulty is when the doubling index is large. So how can we deal with that situation? So for us, a complex unit is when we have a ball and a harmonic function where the doubling index is large. A general idea is to break this into many simple units. A simple unit for us is a ball with a small doubling index and 0 at its center, because in this simple unit, we precisely know what the nodal volume is up to constants. But the question is this even possible theoretically? It is possible because we can go to each 0 and look at balls around this 0. So we saw that if we take smaller and smaller balls, this limiting doubling index is just the order of vanishing of u at this point. And we already said that for most of the points, it's going to be 1. So if we throw out the singular set, we can cover the zeros by small enough balls which have a bounded doubling index. But if we want to use this idea to get any information or estimate for the nodal volume, we have to know what are the radii of all these balls. So let's reformulate this question so that it becomes easy to analyze. So sometimes instead of balls, we'll take cubes, because it's easy to take a cube and subdivide it into smaller subcubes. So start with a unit cube and let's chop it into smaller subcubes of side length 1 over a each. So we ask these two questions. How many of these subcubes have a 0 of u? And what is the distribution of the doubling index in all these subcubes in terms of the doubling index of this large cube? So why is this idea related to what we saw here? So in this case, what we did is we fixed the doubling index and we let the radii vary. In this situation, we fixed the size of all the subcubes and we are asking for what is the distribution of the doubling index. So these are like very closely related. So let's see how Donnelly and Pfefferman use this to get a lower bound of square root lambda in their situation. Let me recall what is the setting. So they have a real analytic manifold. So this picture is the nodal portrait of a lambda Laplace eigenfunction. So assume that this is a unit cube. They divide this unit cube into smaller subcubes of side length 1 over square root lambda each. So this is the wavelength scale. So there are two main ingredients which go into showing this lower bound. The zero density, which is again a simple consequence of Harnack's inequality. So this says that the zero set will intersect each of these small subcubes. But so this is an easy consequence. The main part of their argument was the distribution of the doubling index. So they showed that in at least half of these subcubes, the doubling index is bounded. So in at least half of these subcubes, the doubling index is bounded and we have a 0. So they are like simple units. And we know precisely what the nodal volume in each of these simple subcubes is going to be. So this is going to be the scale, which is like 1 over square root lambda to the n minus 1. And there are square root lambda to the n many of these subcubes. Half of them are simple. So that is how we get a lower bound of square root lambda. So why can't we use the same idea for harmonic functions? So firstly, the second statement still holds for harmonic functions. If we look at scales 1 over n, where n is the doubling index of the harmonic function, this statement is still true. But the problem is there is no analog of the first statement for harmonic functions. So while it might be true that half of these subcubes have bounded doubling index, it might happen that they also do not have any zeros. So we can't get any estimate for the nodal volume. But this gives an idea of what we need to understand to estimate the nodal volume. So we need to understand two things: where and how to find zeros of harmonic functions, and what is the distribution of the doubling index as we come down scales, or if we take a cube and we chop it into smaller subcubes. So a quick answer for the first question is Harnack's inequality. So in the rest of the talk, I want to focus on the second point because this is the main difficulty. All right, so I think nearly 20 years ago, Nazarov, Sodin, Pultrovich, when they were thinking about similar questions, they realized that if we want to understand the zero set of harmonic functions or Laplace eigenfunctions, it is crucial to understand the additivity properties of the doubling index. So here is a related conjecture. If we take a unit cube and divide it into, say, smaller subcubes of scale 1 over a, where a is a large number, but it is much smaller than the doubling index of u in this cube. So the conjecture is the average doubling index of the small subcubes comes down by a factor of a. So I think this conjecture can be attributed to all the 5 names appearing in the slide. So again, Sasha was the first one to make progress on this conjecture. He showed that the doubling index comes down by a factor of a to the epsilon for some small epsilon. Or simply put, if you take a cube and divide it into smaller subcubes, most of these small subcubes have a doubling index which is much smaller than the doubling index of the large cube. So, this is the main part of Sasha's work. So using this, Sasha showed a lot of things. The first is he resolved Nadrashvili's conjecture. He showed that Nadrashvili's conjecture is true in all dimensions. He also made significant progress in Yau's conjecture. So recall that this is Yau's conjecture. If we have a smooth closed manifold, then the nodal volume of a lambda Laplace eigenfunction grows like square root lambda. So previously, nothing was known about the lower bound, and there was an upper bound. But Sasha proved the expected lower bound. He obtained square root lambda for the lower bound, and he also greatly improved this upper bound. So now what is known as polynomial in lambda upper bound for this nodal volume. Okay, so I now want to give like a very brief idea of the proof of our result. So in this case also, we use Sasha's result about the distribution of the doubling index. So this is the main proposition. Suppose we start with a unit ball and a harmonic function which vanishes at the center of the ball, and say the doubling index of all these balls is n. This is like a very mild condition. So starting with this, think of this n to be really large. So starting with this, we can obtain several small balls such that the doubling index in all of these balls comes down by a factor of a. the function vanishes at the center of all these balls and some other condition. So this can be thought of as a tiny reduction in complexity. So recall what we wanted to do was we wanted to completely replace this by by simple units whose doubling index is bounded. But so far, we only managed to get that the doubling index comes down by a huge factor. So if we want to get like several simple units, it's clear that we need to iterate this argument several times. So let me just say what this third condition is about. So this third condition gives a lower bound for the total scale doubling index. So what this says is, while in replacing this whole ball by just these uh, smaller balls, we are not losing too much of the nodal set. So this total scale doubling index can be thought of as a proxy for the nodal volume. So this is saying that while we start with the scale doubling index to be n, the scale doubling index in of all these balls has not come down much. The doubling index has come down by a factor of a, but this has come down only by a factor of log a. So, like I said, we iterate this argument several times until we get simple units. That is, the doubling index in all of these balls is bounded. And finally, at the last step, when the doubling index of all of these balls is bounded, this quantity here just becomes the total nodal volume in all of these balls. So that is how we get an estimate for the lower bound. So there are still a lot of interesting questions which remain to be answered. So I'll end my talk here. Thank you.
Any questions?
So this n to the 1 minus epsilon, that's for any epsilon?
Yes.
But there was another part where you said there exists an epsilon, but that was as a fixed specific epsilon?
Yes, yes, yes. So that
they're
is,
not-
yeah, they are not related.
Have a little time for another short question. Yes.
So could you do something for, let's say, hypoelliptic operators or some variation of the Laplacian?
Yes. So, so this is, I mean, I just chose the Laplacian so that the representation is simple, but you can do the same for any second order elliptic operators.
How about non-elliptic?
Sorry?
How about non-elliptic? Maybe
Non-
hypoelliptic?
Non-elliptic might be very difficult. I mean, I do not know. Probably it's difficult because all of this, I mean, the fact that we are able to do this is because of the elliptic regularity of
But they
these
still have
functions.
that. Hypoelliptic still have elliptic regularity and they have Harnack.
Okay, what are
Maybe we
hypoelliptic?
can discuss it.
Maybe after the
Oh.
talk. All right, so we will not have a break before the next talk. Immediately start. Yeah, no, I guess we'll bring up the slides if anyone need to run to the toilet.
This room.